This is the third part of our video for section 1.5 of the course, and we are discussing block diagrams, representation, how to represent a dynamic system using block diagrams. It is actually realized in Simulink, the simulation, and how we have to put the system in block diagrams in order to simulate a system. So in block diagrams, we may have multiplication by a constant. This is how it is shown. We have a signal. If we have that square, it means that we multiply it with a constant, and the output is equal to that constant times the input. This is integration, actually. The output is the integral of the input, but in Simulink notation, we put a 1 over s for that. That 1 over s is actually, remember, the Laplace transform of an integral of something. Okay, dynamic systems are represented like this. For example, if we have a system transfer function in this form, this is the input-output equation. I hope everybody can see that. If the transfer function is that, the input-output equation is in this form, because this is ys divided by us. If you multiply ys with that, s square means second derivative, 4s means 4 times first derivative times 12 of the variable. At the denominator here we have us, so us multiplied by that, 3 times the derivative of u plus 2 times u. So that's the input-output equation. Okay, so differentiation in time domain is multiplying by s, remember, and integration in time domain equivalent to dividing by s in Laplace domain. In standard block diagrams, we also have summing junctions shown like this. So if we have two signals coming to that junction, the output is equal to u minus w, because I have a negative sign here. So signs must be provided here so that we know what's happening here. If you don't provide any sign, it means that it's just a summation. Okay, so let's make an example on block diagram. How to represent the DC motor that we have discussed, but we derived the dynamics, and actually we have also put the system in the state space form, remember. Now we will just represent the system in using block diagrams. That is the situation. So how shall we represent the system in block diagram? Okay, before showing you the block diagram, there's one thing that I have to start with. The first thing in starting a block diagram is the input that is supplied. I have an input supplied. That input supplied causes a change in the dynamics in the current. And that current is an input to the dynamics of my mechanical system, and also load torque is an input to the dynamics of the system. So the first thing in the block diagram is that voltage in. Actually, this is the physical, more physical approach to modeling. We just imagine what's happening in the motor. First, I supply a voltage, as shown here. That voltage supplied is acted on the armature circuit dynamics. What is the input to my armature circuit? The En plus, remember that's the back EMF, electromotive force. So En minus back EMF, En minus Kb times W, Kb times omega, excuse me, this is the angular velocity. En minus Kb times omega is the input to the current dynamics. So En minus Kb times omega, which I get it from somewhere else in the block diagram, is the input to my armature circuit. So that's a first order differential equation, and actually the system dynamics is governed by 1 over Ls plus R. isn't it? Because I have here L times I dot plus Ri is equal to input. So if I take Laplace transform, Lsi plus R times Is is equal to input, which is composed of that and that. So my output divided by input is 1 over Ls plus R. So I put it here, 1 over Ls plus R. So that current is multiplied by the motor torque constant, and that becomes my torque created by the electric motor. Okay? And I also have a load torque acting. Now we become this part of the dynamics, the mechanical part. So the input to that is the torque created by the electromagnetic force developed in the stator, minus the torque load, the load that we have to work against. This is the input to the rotor. So that is the output, omega. So output divided by input is my transfer function here. What is it? It is J times S omega plus B omega is equal to US. So my output, which is omega S divided by US, is equal to 1 over JS plus B from that equation. So my input torque from the motor minus torque load is acting as an input to the rotor dynamics, and this is the transfer function of the rotor. So the output is omega. That output omega is also an input, remember, to the armature circuit in the form of back EMF. So actually this is called a feedback line. So what does that mean? Actually, the output of the system is affecting the input of the system. So this is a feedback system. So the block diagram is in the feedback form. The feedback systems are covered actually in control system design that we will discuss next semester, hopefully. But this system is already in the feedback form. Okay. So that is the example. Lastly, we will discuss the standard input functions that we apply to the system, because those input functions, we will use those input functions in simulations. So in simulations, in order to check the performance and in order to analyze the stability of the system, we apply some standard inputs to our models. What are the standard inputs? They are like test signals, test input signals. And many standard input functions have a basis in the realistic dynamic system, actually. In realistic practical situations, we have some similar inputs, so we try them. That is the step input. What does that? It is a constant value all of the time, starting from 0. So it's 0 for time before 0 and 1 for all the others. Or if it's not 1, something else, it is that number times u. That is the ramp input. It's increasing all the time. So input is equal to t. If it has a slope, not 1, but something else, then it is u is equal to a times t. This is called a ramp input. Ramped step input, actually, most of the time we have, in practical situations, we have that kind of an input, because you cannot suddenly increase something at 0 time from 0 to 1. It must be gradual, actually, though that gradual increased time may be very small, it is more close to that kind of an input, ramp step input, you see. So I gradually increase it as a ramp to its steady state final value, and then it's constant. So it's a more realistic representation of a step input, because we need a finite time to reach that step. So it is shown mathematically in this form: a times t between that time, and then after this time it's constant value a. This is a pulse input. What does that mean? It has a constant finite magnitude over a finite time. So its value is 0 for the time before 0. It's a for a finite value in time between t and t1. So this is called a pulse input. Impulse input. The input has a magnitude that lasts very short duration. What is impulse? It's a pulse function where the pulse duration goes to 0 in the limit. For example, if that 0 to t1 interval is very close to, again, very close to 0, but I have the same area, for instance, then the magnitude must be very high. So that is called an impulse input. Remember, in dynamics we have an impulse force, a force applied at a very short time interval. That was called an impulse. And we have discussed impulse response in dynamics. So for example, a constant force of 150 newtons applied in 0.1 seconds. The impulse caused by that is force times delta t, so it's 15 newton seconds. So that's the area of the original pulse function. So units of impulse contain units of time. For a force input, an impulse has newton per second, newton seconds, as you see. That's an example of an impulse input pulse force with, if I have 150 newtons for 0.1 seconds, or I apply 300 newtons for 0.05 seconds, the areas are the same. They are both 15 newton seconds. So they have the same area. Okay, we also define a Dirac delta function, a unit impulse represented in 0 time nearly. Okay, we show it like that: 15 delta t. 15 delta t means 15 newtons applied at a time equal to in 0 time. So that's an imaginary type of impulse actually applied at a duration of 0. It is again 15 newton seconds, and the unit is 1 over seconds. The delta t has a unit 1 over second. Okay, so that has a unit of force, 15 newton seconds times 1 over seconds. So Dirac delta function has a unit of 1 over seconds. Maybe we also have sinusoidal inputs. For example, my input may be like this. We will discuss this sinusoidal response of the systems to this sinusoid under a separate section, which is the last section in our course, under the part frequency response. If the input is a sinusoid, what would be the output? You see, this is applied at 0.5 Hertz. What does that mean? The period of that is how much? It is 2 seconds. So frequency is 1 over period. Okay, that concludes our section. See you in our next